Video, we are going to talk about the electronic configuration of atoms. Uh, in the previous video, we talked about the electronic configuration of principal quantum shells. The quantum number 1, 2, 3, 4, n is equal to 1, 2, 3, and 4. In this video, we are going to talk about how to arrange the electrons and entire atoms into these quantum numbers and in the 1s, 2s conventional way of writing 1s, 2s conventional way of writing the electrons in the electronic configurations. Okay, in order to write down the electronic configuration of atoms, there's a principle that we need to know, the Hablas principle. Well, we don't need to know the name of the principle, but we do need to know how to apply it. It says that the electron will enter the orbitals at lower energy first, and this makes total sense because entering at a lower energy orbital requires lesser energy, and hence it is easier to enter the lower or energy orbital. So electron will enter the lower energy orbital first by using lesser amount of energy. According to the Aufbau's principle, the 1s orbital has the least energy, then followed by the 2s orbital. This entire chart is basically an energy chart of for the orbitals. So 1s has the least energy and 7s over here has the greatest energy in the given orbitals. The energy level increases as we follow the blue arrows. So the 1s orbital has the least energy. So electron will enter the 1s orbital first. So in order to fill the electrons in each orbital, just follow the blue arrows. The 1s orbital will enter the electrons will enter the 1s orbital first, followed by the 2s orbitals. Then the 2p orbitals are going to be filled according to the arrows. Then 3s, then come over here 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 6s, and 4f, 5d, 6p, and 7s. Okay, so let's write it down. I've written them over here. So 1s, 1s, 2s, 2s, then 2p, then 3s, 3p, 4s, 4, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, and 7s. In the past year papers, I've seen questions being asked up to 4p, sometimes 5s, but most of the times, in 90% of the questions, they've asked, maybe 95% of the questions, they've asked the electronic configuration of elements that end up at 4p, 4p being maximum. Okay, so it's important to know the electronic configuration till here at least. Okay, now we are going to apply the Aufbau's principle to write down the electronic configuration of some elements. The first example over here is sodium 11, which has 11 electrons. Okay, so according to the Aufbau's principle, the electrons will first enter the 1s orbital. 1s orbital. So let's write down 1s first. Okay, out of the 11 electrons, only 2 electrons can be accommodated in the s orbital because s subshell has only one orbital as we've discussed in the earlier videos. Then the next orbital that's going to be filled will be the orbital of the 2s the 2s orbital is going to be filled next. 2s is written. Again, the s subshell has a maximum of 2 electrons. So out of the 11 electrons, 4 electrons have been taken care of. Remaining are 7 electrons. After 2s, the 2p orbitals are going to be filled. So let's write them down. The p orbitals can have a maximum of 6 electrons because the p subshell has 3 orbitals. Then after 2p, okay, so up till now we've taken care of 10 electrons. Only 1 electron is left. 6 plus 2 plus 2 is 10. After the 2p, the 3s orbital is going to be filled. We are left with only one electron, so just write the one electron over here. This is our electronic configuration of sodium atom. Next is chlorine. Again, follow the Aufbau's principle. The 1s is going to be filled first. 1s has a maximum of 2 electrons, so the 2 comes in the power. Then the 2s, 2 electrons, and the 2p, 6 electrons, 3s, 2 electrons, 12 electrons have been taken care of. After the 3s comes the 3p orbital. Okay, 12 electrons have been taken care of. 17 were total, so 5 electrons are left. The 5 electrons can be accommodated in the p orbital because p has a maximum of 6 electrons. It can accommodate 5 electrons. So this is the electronic configuration for chlorine 17. 17 electrons actually, chlorine atom. Okay, then after this comes the sodium positive ion. Okay, in the sodium positive ion, in case of anions, we know that the electrons have become, in positive ions, the electrons are going to be less than the protons in the atom. So the protons are 11, the electrons are going to be 10, 1 minus. 10, 11 minus 1 would be 10 electrons. Now we just have to write, okay, there's a general rule to be remembered that electrons are always removed. Electrons are always removed from higher quantum numbers. So basically, in formation of the sodium positive ion, the highest quantum number is the 3s. So the 3s electron, this electron will be lost, and the 1s2, 2s2, and 2p6 will be the electronic configuration which is left of the remaining electrons. So 1s2, 2s2, 2p6. This is the electronic configuration of sodium ion with one less electron. Okay, then comes the iron. Again, the Aufbau's principle is going to apply. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, till now we've taken care of 18 electrons. And 4s2, according to the Aufbau's principle, after 3p comes 4s and then 3d finally. So 3d, uh, 10, 11, 12, 18, 20, 3d, 6. So this gives a total of 26 electrons. Again, formation of iron 2 plus ion. Okay, this is a very important step, guys. Over here, in the formation of iron 2 plus ions, the 2 electrons have been lost from the iron atom. As I said earlier, that electrons are always removed from the higher quantum number. In this case, although 4s is at a lower energy level compared to the 3d, but it has a higher quantum number. 4 is greater than 3, right? So these electrons are going to be lost. 1s2, 2s2, 2p6, 3s2, 3p6. This entire term can also be written as argon 4. This represents these 18 electrons. Then comes this 4s has been lost in the while the formation of the iron 2 plus ions, and we are left with 3d6 only. So this and this collectively forms the electronic configuration of iron 2 plus ions. Okay, now coming to chloride ions, Cl negative. It contains 18 electrons, meaning one electron more than the protons.